In this quick tip, I'd like to mention four formulas handy for working with angles that are expressed in the radian system of measure or in degrees, and you want to convert to radians. So first of all, how do we convert to degrees if we start out in radians? The answer is that you multiply by the fraction 180 degrees over pi radians. If you think about it, all the way around the circle is 2 pi, halfway is either 180 or pi. So 180 degrees and pi radians are the same thing. This is a form of 1. So we take our angle in radians, multiply it by 180 degrees over pi radians. The radians cancel out and we're left with degrees. If you want to go the other way, that is, it starts with degrees and you want to convert to radians, then you multiply by pi radians over 180. And I'll show you an example of both of those just in a moment. The next one we've mentioned before, the arc length along a circle. If you know this angle here, theta, is the arc length S is given by the radius times theta, where theta must be expressed in radians. By the way, if it's not expressed in radians, then you would multiply it first by pi radians over 180 degrees to convert it to radians, and then you could multiply it by the radius, and you'd have the arc length. The last one is the area within a sector of a circle. The sector of a circle means this. We have a whole circle here, and we have marked out some central angle. That means this vertex is at the center of the circle. And this angle not only subtends a certain arc length, it also encloses a certain area. So it's the area in the shaded region that we want to compute, and that's known as to be theta, the angle in radians, times r squared, the radius squared, over 2. So let's do an example of each one of those, and we'll complete this tip. Let's do an example first of converting radians to degrees. And we're just kind of picking something at random here, but we want it to be nice. So suppose we had 5 pi over 6 radians, and we want to convert that to degrees. Well, we're always going to multiply by a form of 1. In other words, a fraction that has pi radians on one side and 180 degrees on the other, since 180 degrees is equivalent to pi radians. So this is equivalent to 1. Now we put the radians in the bottom this time because we want them to cancel out. So we've got a radian on the top and the bottom. In this case, we have pi on the top and the bottom. That cancels out. So we have 180 divided by 6. That's 30. 30 times 5 is 150. So we have 150 degrees. Now, if we convert back the other way, we should get back to 5 pi over 6, right? So how about if we do that as an example? Go from degrees to radians. So if we start with 150 degrees, we want to convert that to radians, so we'll say pi radians are the same as 150 degrees. 180 degrees, I should say. So in this case, the degrees cancels out. We have 150 over 180 times pi. Now that was supposed to come out to be 5 pi over 6, right? Well, it will if we keep working on it. Let's take the 150 and the 180, divide them both by 10, so I get this down to 15 over 18 pi radians. And then you might notice that both of those are divisible by 5, or rather by 3. 3 times 5 over 3 times 6. So the 3's cancel out, and in fact we do get down to that. 5/6 times pi radians is the measure of a 150 degree angle in the radian system. All right, well, how about an arc length? Well, for an arc length of something like this, you take an angle The center of the angle and the center of the circle have to be the same, of course. And you need to know the radius. So let's just make something up here. Let's suppose that the radius of this circle is 4.2, and try to make it make up something here that's not completely unreasonable. This is not so far from a 30-degree angle, so let's say it's like 25 degrees. Now, if this were already in this, and what we're after, of course, is right along here. This arc length, this distance. Now, if that angle had already been expressed in radians, all we'd have to do is take this times that and we'd be done. But it's not. The angle right now is expressed as 25 degrees, and so we need to convert that to radians before we can do the multiplication for finding the arc length. So we got 25 degrees. We're going to multiply that by pi radians and divide that by 180 degrees. Well, the degrees are going to cancel out. We've got 25 pi over 180. And this will certainly reduce some. There's a 5 in each one of those. So 25 divided by 5 is 5. 180 divided by 5 is 36. And that's it. This is 6 times 6. That's 5. Doesn't factor other than 5 times 1. So I have 536 times pi. Now, that, of course, wouldn't be all that convenient if, say, you were doing some engineering and you wondered how long of a piece of wire you need to map out that distance. So we would convert that to a decimal in most practical situations. So you'd say 5 times pi divided by 36, and that's 0.4363 approximately. And the units here would be whatever the units are along here. So if this were in, say, meters, then this would be in meters as well. Finally, we want to do an example of this one, the area within a sector of a circle. And we already have a picture drawn here, so why don't we go with this one. Again, we'll assume this is a 25-degree angle, and the sector of the circle means this. It's that central point, the center of the circle. You have the initial side and the final side of the angle, and it's also bounded, this region is bounded by those two sides and the circumference of the circle, and so all this area in here. By the way, on the formula sheet, it sort of looks like there's a little bit left out. That's a feature of Microsoft Paint, not of the mathematics. So that part of the area is included in here mathematically. So if we want this area now, the area, that's this sort of shape is called a sector of a circle. So the area within a sector is given by theta times r squared over 2. Of course, you can write these in whatever order. R squared theta over 2 would be fine as well. But the point is the angle is not squared, but the radius is. So we just figured out what the radius, or rather the angle, is in radians. It's 25 pi over 180, or 5 pi over 36. There's the measure of the angle. We would need to divide that by 2, or multiply by half, however you think about it. And then we also need to put on a factor, which is the square of the radius of the circle. We said the radius of our circle is 4.2, so that'll be 4.2 squared. Now, in any practical situation, this kind of an expression is not very helpful. You would want this to be expressed as a decimal. So we'll do that here. We have 5 times pi times 4.2 squared, and then divide all of this by 36 times 2, which is so easy, that's 72. We'll just type it in that way. Okay, and we come up with 3.84. Well, notice if this fell just exactly halfway between 8.4 and 8.5, that'd be 5 with a string of zeros. So it's a little bit more, so we should round this up, 3.8485.